In the previous class, we have seen one way that we can approximate the base filter with the Kalman filter. This was achieved by assuming a parametric class for the model distributions, i.e. Gaussian. This reduces the hard-to-compute integrals in the base filter to simple linear algebra operations. However, this Gaussian assumption does limit the types of distributions that we can represent. A method of approximating general distributions is with the particle filter. Say we are trying to estimate where the duckybot is on a road network based on measurements of landmarks, but we have no idea where we started. This problem is called global localization. The Gaussian assumption is not particularly appropriate here. Instead, we want to track multiple hypotheses. This is the case whenever the posterior belief is multimodal, which is poorly captured by the Gaussian since it's unimodal. Inspired by this, in the particle filter, we're going to represent the belief by a set of particles. Each sample represents a unique hypothesis of the underlying state. Using this approach, we can approximate arbitrary distributions. Let's start by introducing an important tool that we're going to use called importance sampling. Assume that we want to evaluate some integral I over some function f of x, but we don't know how to do it analytically, nor can we sample from the function f of x easily. Now also assume that there exists some other function g of x that has the same support, meaning that it has probability mass at the same places as f of x, in this case represented by d. Finally, assume that this g function is something that we can easily generate IID samples from. With a little bit of mathematical manipulation, we can rewrite this integral as an expectation of f of x over g of x. We can easily approximate this expectation and consequently the integral I by averaging over the samples. In importance sampling, this function g is called the proposal distribution, and the ratios of f over g are called the important weights of the samples. We can represent this by a picture. Imagine we are trying to integrate over this function f. We have this other proposal distribution g. We can sample from the proposal distribution and then weight the samples by the ratio of f over g and average them. As the number of samples increases, this average will converge to the value of the integral over f. Let's apply this idea to our particle filter. Recall from the base filter that this is the complicated integral that we need to evaluate to get the posterior belief at time t-1 from the posterior belief at time t. Also recall that these two conditional probability distributions represent the motion and measurement models. We have moved the measurement likelihood inside the integral since it doesn't depend on xt-1. If we set f to be everything inside the integral, this is exactly the setup we saw in the case of importance sampling. So we just need to define a proposal distribution and a method of sampling from it. A good choice for the proposal distribution that should have the same support as the posterior belief is the prior belief that we obtain after propagating the particles forward through the probabilistic motion model. This gives a proposal distribution that is equal to the posterior belief at time t-1 times the motion model. If we define things this way, then the importance weights will correspond exactly to the measurement likelihood, so we can use our measurement model to calculate them. Now the question is, how do we sample from our proposal distribution? Well, recall that the posterior belief at time t-1 is represented by our particle set. We can use each of these particles and sample their locations at the next time step based on the control input using the probabilistic motion model. These give us the samples that we need. The next step is to update the weights. Since the weights are exactly the measurement likelihood, we can directly calculate them by evaluating the measurement likelihood at the value corresponding to the sample. Also note that, similar to the base filter, we have updated the particle set at time t in a recursive way based on the particle set at time t-1. So we can choose to just continue in this recursive fashion, propagating the samples through the motion model and updating the weights, but we may get to a point where very few particles have significant weight, all the rest have decayed to zero. For this reason, it can be useful to occasionally resample the particle set with replacement, using the weights as the probability of drawing each particle for the new set. This process is called sampling importance resampling. We can add this optional sampling importance resampling step at the end of our algorithm. Now let's take a look at what this would look like in Duckytown for the lane localization task. Again, we will only concern ourselves with the distance from the center of the lane d and the angle relative to the lane phi. Just like last time, consider that our duckybot is placed near the center of the road. We can sample an initial particle set from a Gaussian or a uniform prior. Then we receive a control action which causes the car to move. Our particles will be sampled through the motion model and will consequently disperse. Then we receive an image from the camera and detect a road line in it. We can use this road line measurement to update the weights of the particles, making the ones that are more consistent with the lane marking higher and those that are less consistent lower. Here the weights of the particles are indicated by their sizes. Finally, we might choose to resample the particle set, and many of the very low-weighted particles will not get resampled. A crucial consideration in the case of the particle filter is the size of the particle set. If it is too large, then the algorithm will become computationally intractable. If there aren't enough particles, then we will quickly suffer from particle depletion and potentially lose the correct hypothesis, causing the estimate to diverge. The particle filter is an example of a non-parametric filter. It is particularly useful when the target distribution that we are trying to estimate does not have a nice Gaussian or parametric form, and particularly when it is multimodal.